Hi everyone. Today we study ESA1H numbers in physics differ from those in mathematics. After completing the recording this lecture, it will be uploaded to the 2024 ESA playlist in our YouTube channel. And the PDF file, this PDF file is available at K-pop Digital Library. Its address is kpope.org. In here, you can find table of contents, Escape from Scientific Absurdity, Series A. Click here. Right now, we are looking at this H, and after recording this lecture I will upload this file to the playlist in our K-pop homepage, and the link will appear here next to the PDF file link. And our official homepage of this class is at Naver Cafe, and you can visit there. This is a cafe, naver.com, K-pop. And our discussion will appear in Escape from Scientific Absurdity. Every announcement will be displayed in here. And you can ask me any questions in the Q&A board. All right. Let's go. Number one. Where can I find this file? I told you already. This series of lectures is Escape from Scientific Absurdity, given at Korea University in the spring semester 2024. You can find this PDF file at the K-pop Digital Library. Its link is given in here. The official homepage of this course is the K-pop Naver Cafe, and the link is always on top of the PDF file. Any questions regarding this lecture are welcome, and please leave your inquiries to the K-pop Naver Cafe in here. What is the version H? We work on based on the version A, Series A, that can be found. Wait a second. Escape from Scientific Absurdity, Series A. Last year we studied Series C, so the student told me it's rather difficult, as I have downgraded the version to version A. The version H stands for the helper version to prepare the beta test. Everybody knows that we have every class we take 10 beta tests. So a single test consists of 10 questions. This version would help students who have less self-confidence in physics and math. If you're familiar with physics and math, then you don't worry about too much about what is written in the H version. Okay, the first topic is the symbol X in physics and mathematics. Perhaps you're familiar with the letter X. Usually it is written in italic letter, and in mathematics textbook it appears as a solution of some equation. For example, x squared minus 1 equals 0. It has a solution x equals plus minus 1, something like that. Okay? However, in physics, in comparison with the x appearing in mathematics as a real number, usually a real number, in physics, x stands for the position or displacement. The position is, for example, in the one-dimensional Euclidean space, we usually introduce a number line, choose the reference point as the origin, standing for number 0, and the unit 1. As soon as you choose these 2 points, then any point on a straight line has a 1-to-1 correspondence with a real number. So once you define a reference point, and any point can be expressed as a multiple of a unit length. But in mathematics, every physical quantity loses its own physical dimensions. So this number line does not stand for exact position in space. Instead, it's a position in mathematical imagination as a number. No scale is present there. However, in physics, a position has a certain scale of length. For example, we use a centimeter or meter as a unit of length. While position stands for a single point on a straight line, if we consider a point in a one-dimensional Euclidean space, the displacement stands for the difference of the position. Difference of position is you need to find the starting point and your destination. So we choose a point A to point B, and point A has some number, for example 2, and if we have number 4 standing for point B, then the displacement from A to B is the 4 subtracted by 2, that is 2. This is the displacement, the change in the value of the position. That is called the displacement. So we can generalize this idea to the three-dimensional space we are living in, and we introduce a quantity that's a mathematical quantity based on the originating from the displacement in space as a vector. A vector has a very similar algebraic structure as a real number. Instead, it has dimensions, mathematical dimensions. You know, a straight line can be expressed as a single real number, and a point on a plane, for example, we introduce the x-axis and then y-axis, and to represent the point on a plane, and you have x comma y. There's the Cartesian coordinates of the horizontal and vertical axis, and using these two real numbers, you can identify a point on a plane. To express this, we need to extend the idea that we studied, that we learned from out of the one-dimensional objects. So extension to the two-dimensional and three-dimensional case for the change in the position and relative position of 2 points is expressed as the displacement, and that displacement is not restricted to a real number, but it is extended to a vector that is 1, 2, or 3-dimensional object. In abstract algebra, we can extend this idea to the more general case, n-dimensional Euclidean space, but our major concern in here is what about x? X stands for usually a real number that is a solution of an equation when we study mathematics. However, if we study physics, X is usually the position or either position or displacement. And that displacement is generalized to study a vector in a plane, on a plane, or in space. While mathematical number, a real number, is dimensionless, any physical quantity has its own physical dimensions. For example, length, time, mass, something like that. And powers and products of them can acquire some physical meaning. So we have to be very careful to distinguish physical quantities from pure mathematical number that is always dimensionless. Number 4, scalar or vector. The simplest physical quantity is a scalar. We know time t, position x, mass m, they are all scalars. Any physical quantities are written in an italic letter. And if we introduce a very bold-faced italic letter or italic letter on top of it, it carries an arrow, then we denote them by vectors. Any scalar, for example, in mathematics, real numbers, they are scalar. In physics, there are various scalars. Time, position, mass, all of them can be expressed as a real number in units of a physical quantity. That is called a unit. And we have a standard international unit system. I have provided various links for elementary information that can be obtained from Wikipedia. So if you're not familiar with each new terminology, then why don't you click this to study more? Okay, any physical quantity is expressed as an italic letter in Roman. Let's compare this. This Roman letter M stands for a unit. This M italic letter stands for mass. So be careful. Any letter in Roman in physics should be either a unit or something like number. For example, kilogram. Gram is a unit and kilo is 10 to the 3, 1,000. So a Roman letter, it is, we call them prefixes, and then a prefix stands for a number, this decimal number, and a Roman letter stands for a unit. If you have an italic letter, then usually it is a physical quantity that has its own physical dimensions. And those dimensions are products of powers of length, time, and mass. All right? As I told you, bold italic letter or an italic letter, on top of it, it carries an arrow, then it is a vector. Vector has a magnitude and direction. Number 5, what is the origin of vector? A vector, it carries a magnitude, and with an arrow, we indicate the direction of change. So this is a vector, and simplest vector is a change in position from one single point to another point. This arrow, the magnitude length of this arrow stands for the magnitude of this vector, and this arrow shows the direction. There are many vectors with the same magnitude, and all of these vectors are different even though the magnitudes are the same. Even if their magnitudes are the same, because the directions are different, we say these vectors are different. So 1 kilogram does not have any directional information, so it is a scalar. It can be expressed as a product of a real number and the corresponding physical unit. In here, position or displacement vector, all its a time derivative velocity, that is the time derivative of the velocity. These are all vectors, and these mass, time, temperature, and so on, the single real number in units of physical reference of physical quantity is called a scalar. What is the mathematical dimension? So you must be familiar with dimensions from middle school to high school. And a point on a straight line represents a point in one-dimensional Euclidean space. And two-dimensional Euclidean space can be constructed on the xy plane. And a point in three dimensions can be expressed in terms of three independent real numbers. Those numbers, for example, in one dimension x, in two dimensions x comma y, and three dimensions x comma y comma z, these are called the Cartesian coordinate, named after Descartes, the Cartesian coordinate, x, xy, xyz. So for a single number, we don't have to introduce a parenthesis. We use just a single number for a point on a straight line. Into dimensions, we must distinguish the two numbers. So one is x coordinate, horizontal coordinate, and the other is a vertical coordinate. So x and y. So this x and y, horizontal axis and vertical axis, they are distinguished from the other. So x comma y can be expressed as shown here. X comma y is a sum of x comma 0 and 0 comma y. And this one is a product of x, a real number, and this is a unit, and unit vector, because it is a two-dimensional case, the number and unit. And this is a unit along the horizontal direction, and this is a unit arrow along the vertical direction. And because if we add these two, we can get 0, 0, if and only if both of them are 0. So these Cartesian coordinates are uniquely defined. If we express a point as a linear combination is two vectors multiplied by real numbers and sum of them. This is called the linear combination. Any linear combination becomes 0 if and only if both coordinates are 0 simultaneously. So this way of representing a vector in terms of basis, they are linearly independent. So this uses the basis makes the representation of a vector in terms of coordinates and that are uniquely defined. So that's the reason why we learn these Cartesian coordinates from elementary school to high school, and still we are learning. The three-dimensional extension can be expressed in such a manner. X comma y comma z is a linear combination of three unit vectors along the x, y, and z axis, and we multiply corresponding Cartesian coordinates and sum them all, and this is a linear combination of three linearly independent vectors that are basis vectors. For convenience, magnitude of these vectors are chosen to be unity. Another way of expressing this, because it is too busy, we just say this is a unit vector along the x-axis, unit vector along the y-axis, unit vector along the z-axis. Here the hat represents the fact the magnitude of this vector is 1, unity, so it is a dimensionless. This is magnitude. It indicates the direction only. Magnitude of this vector is represented by these coefficients. And later we will learn that by applying Pythagoras' theorem twice, the magnitude of this vector will be identified to be x0, x squared, y squared, z squared sum square root. All right. So this vector index 1 represents, it is parallel to the x-axis. Index 2 represents the fact that this vector is parallel to the y-axis, and this 3 represents the fact that this vector is parallel to the z-axis. Invariant or covariant. In nature, there are many physical quantities that do not change independently of time development. So in that case, we say it is invariant. As well as depending on independence of time, we can also introduce the independence of a quantity not depending on time change, but depending on the translation, rotation, so any kind of transformation. We can also say some physical quantity is invariant under some transformation. On the other hand, some quantities may vary depending on a transformation. But once we can identify the systematic rule of changing the value of a physical quantity, then we say it is varying covariantly. So if you know what happens to the mechanism of changing a physical quantity, then we say it is covariant. So one of the most important invariant quantity is the speed of light, from which we can derive Einstein's special theory of relativity. Okay, that's it for today. Thank you.